It flew without wings, and from the moment it appeared, the mystery began.
We have an object that presents very advanced technology.
In March 2025, a perfect metal sphere fell in Buga, Colombia, seamless, ice-cold to the touch, and somehow able to change its own weight. Within days, Russian physicists called it a time capsule, not for storing messages, but for teaching physics we haven't discovered yet. 48 hours later, those scientists went silent. No more data, no more emails. The object is now under restricted study, and what's been recorded so far should not be possible. So what exactly did they touch? Was found. Witness videos showed a round metal object about 50 centimeters across resting on a field outside Buga. Local officers set a perimeter, loaded the sphere into a crate, and moved it to a university lab for basic checks. Photographs showed a clean surface without burn marks, dents or scratches, and no screws, welds, ports or hatches. Radiation and explosive tests were negative. A handheld thermal camera showed the surface a few degrees below the air, and the reading stayed stable in shade and sun. Because the object did not match normal debris, national labs offered help, and a Colombian university team began X-ray and CT scans. The images showed that the sphere was not hollow. Inside were several concentric shells, a central dense core, and many curved channels that linked the layers. At least 18 small internal spheres sat at fixed points in the network, and some channels looked like optical paths with smooth walls. The internal layout was orderly and repeated with symmetry. There were no moving parts, no loose fragments, and no cavities for batteries, pipes, or tanks. The outer shell was thick and uniform. Materials tests reported an aluminum-based alloy with trace elements that are common in aerospace metal, but the hardness was far above ordinary grades. The lab could not find a seam or any sign of assembly. That raised a basic question. How were the internals placed inside a continuous shell? Additive manufacturing can print metal and build internal features, yet printers that large leave texture marks and tiny voids. This shell looked cast or forged and then polished to a mirror state, yet casting cannot create long, clean optical channels. No single known process explains both the smooth hard shell and the complex interior. During handling, several staff said the sphere resisted pushes as if it slid with less inertia than its mass should produce. That is a subjective claim, so the lab scheduled controlled tests with drop rigs, torsion devices, air bearings, and video. Before those results were shared, a Russian group arrived with their own instruments and a different plan. So what did they see that made them choose silence instead of open science? A device that teaches by doing. The Russian team did not claim time travel. Their time capsule phrase meant a device that teaches by how it behaves. They argued that a builder who wants to pass knowledge across language and culture can encode lessons inside measured effects. No text is needed, and no symbols are needed if the device forces the observer to learn by testing and modeling. They used a simple example. If you hand a working transistor radio to a person from 3 centuries ago, the parts force new ideas. That person sees diode coils, and a printed board builds tools to measure current, and voltage invents terms and laws, and learns by reverse engineering. The radio is not a book, yet it teaches. The sphere, they said, is the same idea, but at a level beyond our present tools. If mass appears to change, then mass is not fixed in practice. If temperature drops without coolant, then heat can move in ways we do not expect. If inertia drops under some conditions, then motion can be shaped, not only pushed. Their field plan used plain goals. First, record mass over time with traceable instruments under stable conditions, and include matched dummy spheres. Second, log heat exchange with high-grade sensors in sealed and open chambers, and confirm with calorimetry. Third, test inertial response with calibrated drop rigs, torsion balances, and isolated stages, and record with high-speed video. Fourth image, the interior at higher resolution using multi-energy CT and phased array ultrasound to check for hidden cavities. Fifth, record every step with an open chain of custody and share raw data so other labs can check the numbers. They also asked for blind trials so that analysts would not know which sphere was real during a run. They suggested that a true teaching device would respond the same way in many labs. They posted the plan and asked for partners. 2 days later, their social feeds went silent, and emails bounced back with server errors. But if the object was made to teach, then what exactly is it trying to teach inside the shell? CT scans and ultrasonic maps showed several concentric shells separated by thin gaps with curved channels between the layers. At least 18 small internal spheres sat at fixed points inside the network, and a compact core with higher density than the rest of the metal sat near the center. Many channels are linked to that core. In a normal product, those channels might be wiring trenches, coolant lines, or waveguides. In a sealed metal sphere with no ports, the channels look like a structure for routing fields or heat. The outer shell hardness exceeded 300 on the Brinell scale in some tests. Bulk aluminum that is hard is rare and usually brittle, yet this shell did not chip under controlled impact or deform under lab loads. The surface finish was consistent to sub-micron roughness, and no tool marks were found under a microscope. Several engineers said the shell looked grown or formed in a single operation with very fine control and then polished. That is far beyond common production. Even defense labs that machine seamless housings for sensors leave microscopic marks or slight ovality, and those were absent here. Additive metal printing can place complex internals, yet the largest electron beam and laser powder systems cannot produce sealed half-meter spheres with this purity and finish. They also cannot embed long optical channels inside dense metal without slag or occlusions. Casting can produce large, clean volumes, yet then you cannot place the internal network. Segment builds, joined by diffusion bonds, would leave seam evidence and property gradients, and those were not seen. Chemical vapor deposition can form ultra-clean layers, yet that route is slow and not known at this bulk size. The density maps suggested layers with slightly different acoustic speeds, which could be engineered laminates. Those may form a metamaterial for heat vibration or inertia control. If so, the device is not a container. It is a field shaper. It may route heat or inertia, the way fiber optics route light, and that would match the cooling and inertial claims. It would also explain why no ports exist if the unit works by shaping fields inside a closed shell. That picture remains a hypothesis until higher resolution scans confirm the exact layout. The core region drew special attention because its size and density suggested a different material or a dense lattice. Spectroscopy through thin windows in the shielding hinted at aluminum with unusual ordering rather than a heavy element. If true, the higher density might come from packing or from a composite with ceramic phases. Engineers considered whether the small internal spheres could be resonators or phase references that helped the device keep a stable pattern. They sat on lines that matched nodal curves in the acoustic maps. That layout looked like deliberate tuning. One worry raised by the team was that strong fields could exist inside the shell. To be safe, they tested for stray static shock and for induced currents in nearby loops. No hazards were found under lab conditions, but the warning remained in place and the team kept insulated barriers around the test area. Which leads to the next point. If the sphere is the machine, what is it doing to gravity, heat, and inertia? What the measurements showed. A preprint by physicist Patrick Morcillo and colleagues documented 3 headline results. First, mass readings increased by about 8.1 kilograms over 36 hours, while size and composition stayed constant. The logs included timestamps and control runs with identical dummy spheres. Scales were calibrated against national standards and cross-checked with different instruments. Second, thermal sensors showed the sphere absorbed heat from the air at roughly 100 watts for long periods, with no power input and no visible state change. The surface stayed cooler than the room, even as the room warmed. Third, in an inertial reference platform, the sphere showed motion without exhaust and a reduced effective inertia in drop and oscillation tests. The team reported an inertial shielding factor as high as 81%, depending on orientation. The team addressed common sources of error. They monitored humidity and airflow, used Faraday shielding and battery power to avoid electrical noise, logged all contacts and movements, used video and dual sensors, and repeated tests at different times of day and in different rooms. They included raw logs and calibration files, so others could check calculations. Still, a single lab cannot settle effects like this. Independent replication at several metrology and calorimetry centers is needed. Until that happens, the results remain unconfirmed. If the mass result is real, then the device may be changing, binding energy or coupling to fields in a way that changes how scales respond. If the cooling is real, then the device may be pumping heat into another degree of freedom that is not local temperature. If the inertia change is real, then the unit may be shaping space or momentum flow on small scales. These ideas do not match standard models, yet small windows in advanced theory allow related behavior. Cold atom experiments have produced systems with effective negative mass. Condensed matter systems often show effective mass that differs from bare mass because of interactions with a lattice. General relativity allows mass-energy exchange through curvature and stress. None of these facts proves the sphere, yet they show the ideas are not nonsense, because such a device would have clear use in flight energy, and sensing it would draw intense interest from defense and space agencies. Public budget notes show steady funding in topics with names like metric engineering, inertial control, and quantum vacuum. That is not proof of a link to the sphere, but it shows the topic sits at the edge of mainstream research and national strategy. To move beyond first claims, the paper also proposed a replication ladder. Level 1 would confirm simple weight change with 2 scales and a dummy control over a week. Level 2 would confirm cooling in a calorimeter with sealed power accounting. Level 3 would confirm inertial effects on an air table and in a drop tower with high-speed video and independent timing. Level 4 would repeat all 3 at a national standards site with outside observers present. Only after levels 1 through 3 were passed would any team request level 4. This staged plan helps avoid hype and protects scarce time at standards labs. The authors also listed failure modes to watch for, including convection drafts, buoyancy shifts, thermal gradients, scale drift ground loops, and bias. They asked others to add more failure modes so that all teams would share the same checklist and avoid classic traps. If a device can lower its own inertia, move without burning fuel, and dump heat without a radiator, which country would let that stay public? Why access matters. When data moves from open to closed, trust falls. The fastest way to settle the sphere debate is joint tests by several independent labs with full transparency. That means a National Metrology Institute for mass, a top calorimetry center for heat, and a precision inertial lab for motion. It also means dummy units that match size and mass within tight tolerances, so that labs can run blinded trials. Each lab should pre-register its methods and publish raw logs and calibration files. Chain of custody must be tight, with video of each handoff and seals on the crate. There are safety steps as well. If the device moves heat in unusual ways, the lab must set limits to prevent rapid local cooling that could harm equipment or staff. If the device alters effective inertia, drop tests must be contained to prevent rebounds. If the device moves on its own, chambers must be closed and shielded. All power sources in the room must be logged and filtered, and magnetic and radio backgrounds should be recorded. None of this is exotic. It is careful lab work that any high-level facility can do if given time and a clear plan. If access cannot be shared, then a neutral panel should be formed with members from several countries who can review raw data under non-disclosure and issue a joint statement on what was and was not seen. That is not ideal, but it is better than rumors. The world has experience with shared inspection of sensitive objects, and it can be done here without disclosing design secrets. The silence from the Russian group may have simple causes. They may be under orders or repeating tests, or they may be wrong and trying to fix their work before speaking. Silence alone is not proof of anything. The only proof that matters is independent, repeatable measurement. Until then, the right public posture is steady and patient. Ask for data, ask for replication, and keep the focus on test plans, not personal claims. The access plan also covered legal and ethical issues. If the device is human-made and sensitive, then tests must avoid publishing trade secrets. A public panel can publish results about effects without posting microstructure images that would reveal a process. If the device is not human-made, then the panel must decide who owns it and who carries risk for testing. The plan suggests a rotating custody where a neutral facility holds the object and releases it under bond to labs that meet safety and data rules. Insurance and responsibility would be clear, and no single state would hold the device for long. This reduces tension and encourages honest cooperation. The plan also urges calm public messaging. Updates should use clear numbers and avoid dramatic language. This keeps trust high and lets the public follow real progress rather than rumor. If this really is a teaching device, was it meant for everyone, or was it meant for whoever grabbed it first? What the sphere could mean. If the sphere is a teaching device, then the most important lesson may be that the universe allows more control than we use. Control of heat without coolant could change computing industry food storage and climate control. Control of inertia could change transport and spaceflight by cutting fuel use and improving safety. Motion without exhaust could change how we place and adjust satellites and probes, and could allow long missions with small craft. Those are near-term gains. Longer term, if the internal structure is a practical metamaterial for fields, then engineers will build new kinds of sensors, engines, and power systems. Better thermal control could cut waste and emissions across many sectors. Better motion control could change earthquake testing, vehicle safety, and robotics. A device like this would also force new standards for testing, so that labs can agree on what counts as a real effect. There is also a cultural point. A device that teaches by behavior assumes the finder will test carefully and share results. That is how science works when it is healthy. Open methods, clear data, and honest limits build trust. If we respond with secrecy and rush, we fail the test. If we respond with careful shared work, we pass. The device does not pick a side. We do through our choices about access and method. There are other possible meanings. The sphere could be a human device built in secret. If so, we should still run the same tests, and we should still learn. The sphere could be a misread of ordinary physics caused by subtle errors. If so, joint testing will show that, and the lesson will be about better methods. Either way, the only losing path is to let rumor replace measurement. The patient path is to let many hands test the same thing in clear light. Right now, the public record supports hard points. The sphere exists and was recovered near Buga. Scans show a complex interior with shell channels and internal spheres. The shell is unusually hard and clean. One paper reports mass change cooling and odd motion, and those claims are not yet replicated. One research group that proposed a teaching device view stopped public updates. Next steps are clear and do not require belief. They require access time and care, along with open records. Many viewers ask what a real-world timeline might look like from here. A realistic path would include a month for legal agreements and safety planning, 3 months for level 1 through 3 tests, and another month for outside review. If effects repeat, then a larger second phase would begin with more labs and longer runs. If effects fail, then the result is still useful because it teaches better methods and closes a rumor with data. In both cases, the public gets a clear answer. If effects are real, then training programs will be needed so more engineers can work with new field-shaping materials. Universities would build courses on thermal control, inertial control, and precision metrology. Industry would test small units in data centers, vehicle labs, and satellite platforms. Standards bodies would define safe limits and require alarms and automatic shutoff for devices that can move heat or inertia beyond set bounds. We will track verified lab reports, share plain summaries of new data, and avoid hype when numbers are thin. If you want clear updates as this story develops, please subscribe, turn on notifications, and like this video so the platform shows it to you again. When real replication data arrives, we will break it down in simple terms and explain what it means for science, technology, and daily life. Thanks for sticking with Clear Facts.